Hey everyone, in today's video we are going to do the mathematical derivation of the variational autoencoder. So in the next video we are actually going to implement the variational autoencoder. There's going to be some interesting nuances. I expect that you've already watched my autoencoder video or know what autoencoders are, otherwise you don't really have much context for what we're about to do. But today's mostly just going to be a kind of a mathematical derivation. We're just going to do the math and explore where the VAE loss comes from. The reason we're doing this is, as you can probably get a feeling for this, that a lot of neural network stuff's a bit hand-wavy. Like we say it works because we train a model, it works, it's like ta-da, it looks great, but that's not really helpful when it comes to having some certainty for like why something works. And the variational autoencoder is just one good example where we can directly prove why something works. And that's why I want to explore it. I assume that you already have some background in statistics, calculus, that sort of stuff. I'm going to try to explain the derivation in as much detail as possible just so it makes sense to all audiences. But either way, let's go ahead and get started, and just let's start with recapping what we ended with on the autoencoder last time. The problem with the autoencoder is when we compress our data down, there's no restriction on what that compressed space can look like. So for example, this is the output of what our autoencoder looked like. And we can see that this was trained on the MNIST digits. We kind of have these blobs and it kind of stretches out, and it's not a nice representation. But at least in a two-dimensional space, we can see what's happening and make some sense of it. If we compress to like 20 dimensions, we couldn't really do anything about it. Like the points will occupy strange areas of this 20-dimensional vector space, and it's just not convenient, right? There's not much we can do with it. And this is especially important when we start looking into generative models, specifically the latent diffusion model that we'll be implementing much later, but we'll get there. But we need a more compact and understandable latent space. So let's just skip to the end real quick. This is what we're looking for. If you take a look again, right, this is what our autoencoder looks like, a typical autoencoder. You can see, we kind of have these like whooshes of points, and they're kind of stretching out and whatever. This is what the variational autoencoder looks like. It's nice and circular. Most of the data is centered at the center, and it kind of fans out as you go. And that's because this is trying to model something close to a Gaussian distribution. And so what we're going to do today is explore how do we get a neural network to do this, and what's the loss function, what's the formulation we need to actually pull this off. So let's go ahead and get started. I'm going to do a couple of review things first, just in case you've forgotten or you're unfamiliar. Let's first go ahead and start with the Gaussian distribution. So if you remember, a Gaussian distribution looks kind of like this, right? It's just a simple bell curve, and it's parameterized by two things. You have your sigma, which is your standard deviation, and you'll have your mu, which is your mean, right? So a Gaussian distribution is defined by the mu, the center, and then kind of its spread, the standard deviation, right? Standard deviation. So this is what a Gaussian distribution looks like, and we have a very nice and simple formula for it, right? So let's do a univariate Gaussian distribution. So it's just for a single variable, like you see here. We'd have f(x)(x) is our PDF. It'll be 1 over square root 2 pi sigma squared e to the power -1 half x minus mu over sigma squared. So this is our standard PDF of a Gaussian distribution. We can also do a multivariate Gaussian distribution, so I'll just write that. We won't be touching multivariate today. Nothing changes, it just makes the math more annoying to write. But instead of x being a single number, x is now a vector, right? X is a vector of numbers, so we have a Gaussian vector effectively, and it's a vector of dimension d, let's say, right? So dimension d. Well, this will look basically like 1 over 2 pi. I believe it's going to be d over 2. Check me if I got this wrong, but I'm pretty sure that's right. We have our covariance matrix, right? So instead of just a single, sigma, we'll have a covariance matrix that looks kind of like this, right? And on the diagonal, we'll have our variances, but then we'll also have our covariances everywhere else, right? So something like that. You can look this up if you have any confusion, but we have a covariance matrix. We will take its inverse just like that, and then we'll have, again, I'm going to write it in the XP notation because it's a little bit long, -1/2 x minus mu. We'll have a mean vector, right? So a mean vector representing the mean of every single feature in X, all our dimensions. We'll have our covariance matrix inverse, and then x minus mu transpose. And X is also a vector, right? So it looks something like that. We won't be touching the, we won't actually be writing out the stuff for this multivariate Gaussian when we do the derivation, because it just makes the derivation more annoying to look at and less understandable. So we're going for as simple as possible here. So let's quickly talk about why this is important. We have some Gaussian distribution, but where does it fit in? So again, this is a typical autoencoder, right? You take data, you compress it down, and then you decompress, right? So you have an encoder, and a decoder. And this is your typical autoencoder model. And so you'll have something go in on one end, right? So we can say like a picture of some digits, and you'll have something that comes out on the other end, and you'll have like another picture, right? So basically we're taking an image, or really any data, but I'm just using image as an example here. We take an image, compress it down, decompress it, and we get something on the other end. And then our loss function is a reconstruction loss, right? Reconstruction loss. A good autoencoder can take data, compress it down, decompress it, and the output should look very similar to the input. So we have a reconstruction loss, all sorts of options. We can use mean squared error, we can use mean absolute error, we can use really anything you want, right? So there are all sorts of options for reconstruction losses, but there we go. That's our typical autoencoder. The problem is this stuff in the middle, right? We talked about, and we saw, that the space that these things occupy is uncompact, right? It's kind of random. We kind of have these whooshes and lines, and it's just not a nice distribution to work with. It's not a nice compressed representation to work with. On the other hand, this looks much nicer. Something that I know where all the data is, I know how it spreads, I know all the properties of this here. I don't know anything about this. This is just random. It's whatever the model wants. So what do we do in the variational autoencoder? What makes an autoencoder variational, right? All we're going to do is, instead of just mapping to something, we are going to map to a Gaussian distribution. And then this is going to go to our decoder. Exactly how this happens, how we parameterize it, how we use, we'll see something called the reparameterization trick. We're going to take a look at all of that in the next video. I want to focus today on just kind of what's going on here, right? Just what's going on here. We'll get into some of the more nuances of the implementation next time. But all you really need to think about is we take data now, we compress it down, we want the compressed representation, which we typically call Z. We want the compressed representation to be Gaussian. We want it to be Gaussian, and typically we want it to be standard Gaussian or standard normal, so mean 0, standard deviation of 1. So we want Z to be close to a Gaussian. And then we want our decoder to take our Gaussian data and then decompress back to where it is. So now we had the reconstruction loss earlier, but now we have a new thing. We need to map to a Gaussian. So let's call our input, let's call it X, right? X is what's going into the encoder. And we'll have some X hat pop out on the other end, but we don't really care about that right now. What we want is the probability of Z, our compressed variable, given X, to be roughly standard normal, right? We want probability of Z given X to be a standard normal distribution. And the only way for us to do this is to add a new loss function. We need to add a new, so we had reconstruction earlier, but we need to add a new loss function that will penalize the model such that it knows to make Z close to Gaussian. So we need to somehow do that. And there's actually a couple different ways you can do this, but the most typical way of doing it is something known as the KL divergence. KL divergence, or the KL loss. I'm not even going to attempt to pronounce the actual name, but I'll just call it KL, right? KL divergence. So there we go. We have this. So let's kind of talk about what KL divergence is real quick. If you've never heard of this before, it's honestly really cool. Divergences, there's actually a bunch of them. There's KL divergence. There's also another one called Jensen-Shannon or JS divergence, which we'll see when we look at the GAN math for the GAN stuff later. But a divergence is a way to measure the distance between distributions, right? Which is kind of what we want, right? We have something here. We're going to have a neural network try to estimate probability of z given x. It's going to estimate some distribution, right? Whatever it may be. This is our target distribution. So the loss function should be the distance between these two, because we want to minimize the distance. We want to make sure that our probability of z given x is close to a Gaussian distribution. So again, there's a bunch of ways you can do this, but KL divergence is the most popular method to do this. It is a formula specifically to compute the distance between distributions, and it shows up all over the place. So let's first write the KL divergence and maybe relate it to some other stuff that you've already seen before. So first, how you typically write divergences, they kind of look like this. Let's do the divergence between some distribution P and some distribution Q, just like that. Well, this is going to be the sum or integral, right? But it doesn't really matter. For all intents and purposes, I'm just going to write a sum. It's going to be the probability of x times log probability of x over q of x, right? Or whatever it may be, right? So we have not probability of x, but p of x. Like this is our distribution for p. This is our distribution for q, right? For some x, and we'll just add it up over all x's, right? We're gonna add it up for all x's. So this is our typical KL divergence, right? So there we go. Let's try to relate this to stuff that you've already probably seen before. So this is KL divergence, but let's just rewrite some of this out. What we're gonna do is just separate stuff out. So we know the log of a over b is log of a minus log of b, right? Typical log property. So let's just apply that, right? We have this fraction here, so we can split it up. We can do sum x element of x, right? So then we're going to do probability x log probability of x, and then this will be negative because it's in the denominator, minus again sum x element of x, and now it's going to be again probability of x log q of x. I keep saying probability, it's not probability, it's distribution p, distribution q, right? So there we go. This should look very familiar, right? This here is just our negative entropy, so negative h. This is negative entropy. This is our entropy formula, but entropy formula typically has a negative in the front of it. So that's why, because it's positive, it's negative entropy. And then this is our negative cross entropy, right? The cross entropy is between, basically it's our entropy formula, just entropy between two different distributions. So that's negative cross entropy. So our KL divergence is just our cross entropy, right? Because this negative and this negative will cancel. So cross entropy minus entropy, which implies that our cross entropy, and this is the cross entropy formula we use for everything, for our classification tasks, for language modeling, whatever it may be. Cross entropy is actually just the sum of our KL divergence plus entropy, right? And that's basically it, right? So again, I'm just trying to relate some of the things that you might have seen before to KL divergence. Again, this might be a recap for some of y'all, but it's just some cool ways to connect things that you're learning together. So there we go. We now have our formula for KL divergence, and we're going to use this a ton in the future. There is one property about KL divergence, though, that I want to just briefly prove, and that's that the KL divergence is actually always positive. So what we want to show is KL divergence is greater than or equal to 0, right? So this is important, right? We want to make sure it's greater than or equal to 0. And the only reason we're doing this is because this fact is going to be necessary in the derivation of the loss functions that we're going to be exploring, okay? So let's go ahead and just quickly show that. This is pretty straightforward. So our KL divergence, again, between P and Q, right, is going to be our sum P log P over Q, right? So there we go. That is our KL divergence. Let me just double check. Yep, P over Q. Yep, so there we go. And let's just take one step. Let's just flip these two. So we just have to take a negative out, basically, right? If we add a negative to this, then we can just flip these two, and it's the same thing, right? So we can say this is the same as the negative P log QX PX, right? So it's very simple, right? Because this is log P minus log Q, or negative log Q minus log P, right? So we're just flipping them around. So this is a totally valid thing to do. And what we want to do with this specifically is apply something known as the Jensen's inequality. So before we get to that, let's just first look here. We have a sum over a distribution, and remember, this is the sum over x, right? So these are sums over x. So this is the sum of a something times something else. Well, isn't this just expected value, right? This is just expectation, right? The expected value of x is just the sum of x times the probability of that thing to occur. So in the same way, this is just an expectation. So let's go ahead and write it that way. So this is going to be negative, same negative sign, expectation of log QX over PX, right? Very simply, these two things are just equivalent ways of writing exactly the same thing. This is just an expectation, and the expectation is over our distribution P, right? Because that's the thing we're weighting by. So there we go. Now that we have this, let's remind ourselves, if you've never heard of Jensen's inequality before, it's a really cool property, but basically expected value of f of x is greater than or equal to f of the expected value of x, right? So there we go. And this is true for a convex function, right? For convex functions. And then similarly, it will be exactly the same thing, but less than or equal to for a concave function, right? There we go. So I will put a video, I'll link to a video, a really great video, to the proof of the Jensen's inequality. It's very simple. It's pretty intuitive when you draw it, but I just don't want to go down too many rabbit holes, or this video will end up taking way too long. But we're going to be using this. Basically, the expectation of a function is going to be greater than or equal to the function of the expectation of the original, input, if it's convex. Otherwise, it'll be concave, depending on, or it'll be less than if it's concave. So it just depends on the concavity of your function. The function we're dealing with, we have expectation of some function of this data, right? So expectation of some function of our data. Oops, I closed this. Let me just keep this open. There we go, just so I don't lose track. Okay, so what is log? Log functions look like this. And so this is a concave, right? Concave function. Log is a concave function, which means we will be using the less than or equal to. So let's just write it. So the negative expectation of log of our QX over PX is going to be less than or equal to negative log, right? We're basically swapping the expectation and the function, right? So log expected value of QX over PX, right? So there we go. And this is true, again, because of Jensen's inequality. So there's actually other ways to do this, but we're using Jensen's because I think it's just the most easy way to do it. So that's what we're going with. So there we go. We now have this thing, and all we've done is swap our expectation and log, and we've introduced an inequality because of that. So there we go. So now the next question is, what is this? Well, let's go ahead and do it. This is equal to, right? So this is equal to, this is the expectation on P, right? So we can just go ahead and rewrite it in that sum notation just so it's more obvious what's about to happen. It's going to be log, it's going to be the sum, and this is basically going to be our probability of x times the qx over px, and this is the sum over x. Well, this and this are going to cancel, and the sum over an entire distribution, qx in this case, is just 1, right? The sum over a distribution is 1. So that means this whole thing ends up being 1. So that means you have negative log of 1, and only e to the power 0 is 1. So this is just 0. And so we have shown that this whole expression here that we were dealing with, which was our DKL, which was equal to negative sum probability x log our qx over px is less than or equal to 0. Therefore, DKL, our divergence, must be greater than or equal to 0, right? Because it's a negative sign. So there we go. We have now shown that our KL divergence must be greater than 0, and we only did this just because it'll be necessary for the derivation that we're going to do. Okay, so that kind of pins together a couple things. So we've kind of reviewed ourselves on Gaussian. We took a general idea of what variational autoencoders are, but we're gonna now start digging into that, and we explored the KL divergence, right? So you should have that so far. So now let's just keep this moving. Before we talk about the variational autoencoder in more specificity, let's talk about variational inference, right? So what is variational inference? So variational autoencoders in Inference. Variational autoencoders is basically a way of doing variational inference, and this leverages something called Bayes rule. So I hope you've seen Bayes rules before, but we're gonna do a super quick recap on it. So here's Bayes rule. If you have some probability, if you want the probability of A given B, let's say that's what you want, we can rewrite this as the probability of B given A times the probability of A divided by the probability of B. Right? So this is very simply Bayes rule. And we have names for actually all of this stuff. We call this A given B is known as the posterior. And it's typically the thing that we want, but we can't actually compute, and we'll see why. This B given A is typically known as the likelihood, right? Likelihood. Probability of A is typically known as the prior, and probability of B is typically known as the marginal, right? So we have names for all of these things. So let's consider, again, what we're trying to do. We have an autoencoder. It's going to compress down to some z, and then we're going to decompress back, and we'll have x here, and we'll have some x hat that we're trying to predict on the other hand. So we can ignore that for now. What we want is z. So this z, again, is known as a latent variable, right? A latent variable. And what we want to compute is the probability of z given x, right? Something that computes this, right? We want to map to z given x. So again, let's go back a little bit. What is variational inference and why do we do it is the idea, is what I want to discuss. So variational inference is a method of estimating a complex distribution with a known distribution. And so what I mean by that is, let's just take MNIST for example. So MNIST, I know it's a very simple example, but I think it just makes it clear. We have 28 by 28 pixel values, right? 28 by 28 pixel values, or dimensions on this image. So this is really a 784 dimensional vector, right? If we flattened it like we do for the linear autoencoder stuff, if we flattened it, it's a vector of length 784. And the question is, and we're going to call this x, what is probability of x, or the distribution of x, right? What is the distribution of x? And you probably can't come up with something. There's probably no known distribution out there that I can use to just easily say, oh, this is a Gaussian distribution. Oh, this is a gamma distribution. Oh, this is an exponential distribution. No, we can't do that. I have no idea what probability of x is, and or what the distribution of x is. And so that's exactly the problem. And so what we're going to do is say, okay, I may not know what p of x is, but can I learn p of z given x, some conditional distribution where I map my data x to some known distribution, and z can be anything you want it to be. It could be gamma, exponential, it can be beta, it can be anything you want it to be. But in standard VAE form, we will be mapping this to a Gaussian, which is why we started with talking about Gaussians, right? So we'll be mapping to a Gaussian. So probability of z given x must be a Gaussian distribution. Is what that's what we want it to be. We're going to restrict it to be a Gaussian distribution. And so we're going to try to use z, which is going to be some Gaussian thing, to estimate x. And that's the big idea. And the part that makes this an autoencoder, like where does the neural network show up? You can imagine the mapping between our high dimensional unknown distribution data x to a known Gaussian distribution will require some effort. And the neural network's goal, and specifically the encoder's goal, right? The encoder's goal is to learn that mapping, right? To learn some mapping using the nonlinearity and high representation ability of our neural network. And that's basically the key idea. It's a slight oversimplification, but that should give you the general idea. We don't know what our distribution of x is, our data x is, because it's too complicated. And you can imagine this gets more and more complicated as your image gets larger, or your audios get larger, or your text everything gets more complicated as the dimensionality increases and the distribution becomes more and more unknown. So we're hoping we can learn or map to a known distribution, so this becomes an easier task. And that's exactly what variational inference is. It's just trying to use a known distribution to represent a complex or it doesn't have to be high dimensional, but some complex unknown distribution. So there we go. That's the big idea. So now that we have that, let's go ahead and rewrite our problem rewrite the base rule for the problem we're trying to solve. So what we want is the probability of z given x, right? That's what we want. Now, this is not really possible for us to directly solve, and you'll see why in just a second, because when we use base rule, probability of x given z times the probability of z divided by the probability of x. And this is the problem child, right? Probability of x, or the distribution of x, like we just talked about, is intractable. We cannot solve this in any meaningful way, because to find p of x would require us to first have the joint distribution between x and z, and then integrate out over z. So we'd have to integrate over some high dimensional, because even z, even if it's a known distribution, it still could be a high dimensional space. This is an intractable problem. Intractable, right? An intractable problem. And as we kind of start exploring different generative models, you're going to see they're using effectively different tricks to get around this intractable problem, that we can't really estimate x, but can we do it in a slightly different way? And the way the variational autoencoder does it is it uses something known as the evidence lower bound. And so the first step to our derivation is going to be deriving exactly that. What is the evidence lower bound? Or it's also known as ELBO, the ELBO loss effectively. So let's go ahead and do that. So our setup, right? What we're going to do is we will use a, let's call this Q. So let's draw a line here. Let's call this Q theta z given x. So what this is this is a distribution predicted by model, right? Predicted by model. So our model, this is our model, is parameterized by parameters theta. So we're just going to call them theta. These are the parameters of the encoder specifically, right? Those are our parameters. And this is the distribution that our model predicted, Q theta z given x. The distribution that we want, right, is p z given x, which we want it to be Gaussian, right? But this is our target distribution. We will come back to the fact that it's a Gaussian later on. We're going to just do it in general, what it looks like. And then we'll basically just plug in the stuff we need to make it Gaussian right at the very end. So for now, we're just going to just assume that P z given x is any target distribution that we're interested in. Q theta z given x is the distribution that the model predicts via the parameters theta, right? So whatever we use in the encoder, however many linear layers you want, that sort of stuff. So let's go ahead and do that. So what we want to do, our goal, is to minimize the distance between these two things using the KL divergence, right? This is what we predicted. This is the target. So we need to use some type of metric to reduce the distance between these distributions, these predicted and the true distributions, and that's why we're using the KL divergence as our metric. Again, you could use other ones, but the KL divergence is the most common one that you'll see, and so that's what we're going to be using. So we will be doing the KL divergence between first Q theta z given x, right? That's what our model predicted, and then P z given x, right? That's what we want to compute. So to do this, we can do it over, and this time we'll be summing over our latent variable z, right? Because that's basically the target. X is in the conditional, so the KL divergence is happening on z, so we're going to sum over z, and it's going to be Q theta z given x, and then we will have just like before, log Q theta z given x divided by P z given x, right? So again, just referring back to our previous, what we had done, KL divergence, PPQ, right? So it's exactly the same as our KL divergence formula from before, just applied here, right? So there we go. So now that we have that, let's go ahead and start kind of breaking it apart and exploring all the different things that we need to do. So now our first step is going to be just doing some simplification on this, right? So what we have is we have probability of z given x. We want to rewrite this slightly. So if you remember the formula for conditional probability of A given B is the same as writing the probability of A and B divided by the probability of B, right? So there we go. So we're just going to do that. We're going to do probability of z given x. We're going to write it as the joint distribution and just rewrite this a little bit. So what we're going to do is we're going to write the sum z element of z, right? Summing over z, we have Q theta z given x. And then what we're going to do is log, just like before. And instead of writing P z given x, this is going to turn into P z and x, so P z comma x, right? The joint distribution between the two. And then because it's divided, but it'll then go to the numerator, we'll have probability of x up here. And then we still have our Q theta stuff going on. So Q theta z given x, right? So there we go. So that is the first step, right? All we've done is just leverage our typical conditional probability formula, just like before, just like always, and there we go. So now we have that. Now that we have this, we can go ahead and separate some stuff out. So log of A times B is again log A plus log B. So let's go ahead and do that. We can do sum z again, Q theta z given x log. I'm going to keep these two things together, and then I'm going to separate the P of x out. So it's going to be this times this. So it's going to be log of this first term plus log of the second term, right? So we're going to just do it that way. So it's going to be log Q theta z given x divided by probability, the joint distribution between z and x, just like that, plus, right? And we're just going to distribute, again, z element of z, or sum over z. Again, it's the same Q theta z given x. And then we just have our log P of x. And there we go. Now, something I want you to keep in mind is notice this sum is over z, but this expression here has no z, it's just x, which means technically this is a constant in terms of the sum, so we can actually pull this out to the front, right? We can pull it out to the front. So instead of writing it this way, we could have written it like this. We can write it as log p of x, right? Because it's just there. And then we can pull out the sum, and then we just have our regular sum from before. So it's going to be q theta z given x, right? Just like that. Now, notice something here. We are doing the sum over z, and our probability is on z. I mean, there's a conditional, but that doesn't matter. This probability is on z. So that means summing over all the z's on this z means this sum must be equal to 1 just by the total law of probability, right? By total law of probability, this must be 1 because you're just summing over everything, so it must be 1 because distributions must sum up to 1. So we don't really have any of this stuff left anymore, right? This is just 1. So we're just left with this. We're just left with this. And so we can then go ahead and write. And if again, if you remember, what did we start with? This expression was DKL, right? We started with this being our KL divergence. So that means this whole thing is equal to DKL, right? Where we started. Now that we have that, remember DKL, this must be greater than or equal to 0. And that's why we proved at the beginning, this is where it comes in handy. This whole expression here must be greater than or equal to 0. And if it must be greater than or equal to 0, then we can write negative. Here we go. Negative, right? We're just going to flip the sides. Negative z element of z. Negative q theta z given x log q theta z given x over p z comma x, right? It doesn't matter, so there we go. Z comma x. This is going to be less than or equal to log px, right? So again, if this is greater than 0, then I can just take this whole thing, put it there, and just flip it around. So there we go. So we now have this expression, which is what we're going for. Now, z comma x is a little bit annoying for us to deal with, and so we're just going to rewrite it again using the conditional probability formula. And so our final expression is going to be negative sum z element of z q theta z given x log, again, the numerator stays the same here, z given x, but probability of a and b is the same. You can write it in two different ways, but we're going to write it as probability of x given z. We could have also done z given x, right? Because we can go both ways, but we're going to write x given z times the probability of z. We could have also written z given x times the probability of x, but this would have been less helpful for us in the derivation. So you'll see why we do that. So now that we have that, this whole expression, z given x, probability x, is less than or equal to log of p of x. And here is one of the most crucial parts of this whole derivation. Actually, before we kind of wrap this part up, let's put this negative inside the log, right? Just put it in just to simplify a bit. So z element of z, q theta, z given x. And then if we put a negative inside the log, that's effectively just flipping the fraction, right? So we're going to do log. It's going to be px given z, pz divided by q theta z given x. And this is less than or equal to log p of x. Okay. This here, here we go. This here is known as the ELBO loss. This is our evidence lower bound. So let's kind of examine exactly what's happening here. So in typical fashion for maximum likelihood estimation, for example, what you're trying to do is maximize the likelihood of a distribution, right? Or in the case of MLE, you're maximizing the parameters of a distribution, and we'll see exactly where that fits in later, but you're trying to maximize a distribution, right? The likelihood of a distribution. Well, here is the distribution we want. We want the distribution P of X, right? That's our target distribution. Here is an expression we just found, and notice everything in this expression is computable. We know PZ, we can do X given Z, we can do Z given X. Exactly how we do Z given X and X given Z, we're going to see that in just a little bit. But everything in here is computable or trainable by a neural network. This, on the other hand, px, is not tractable in any meaningful way. But we found a lower bound. We found a function, we found something, basically a formula, that will always be less than or equal to the thing that we want, or the log of the thing that we want, but that's fine. Log is a monotonic function, so it doesn't make a difference, right? We don't really care. This is basically it. So as long as we maximize, if we maximize our ELBO, right? ELBO, if we maximize ELBO, then as long as we're maximizing this, then we are also maximizing this effectively. We're still doing this. I mean, you can imagine it kind of like you have your log p of x right here, and then you have your ELBO, which is always less than or equal to. And if I start pushing this up by training a model, then it will push against the true p of x that we want and push this up as well. So maximizing this is the same as maximizing this, because this must always be less than or equal to this. And that's the key idea. Now, how do we actually pull this off? Well, we need to do something specific. Let's first see here. We parameterize z given x by theta, right? So if we go back up, our encoder, right? This is our z given x parameterized by theta. Notice the next expression here, the one on top. This is x given z, x given z. Well, what is that? That is me producing an output given the z. So this is x given z. And this is also a neural network, so why not just parameterize it by some parameters phi? And so what we're going to say is this, and let's erase u, grab u. We're going to parameterize u by phi. So this denominator is effectively our encoder. This is our encoder. And our numerator, this expression here, is our decoder. And that's basically where our neural network falls. Neural network's job is to basically somehow compute these, using training, right? We'll train it to do this specifically. Everything else is known, right? Similarly, this is also trained, right? For the same reason. So we now have everything we need, which means we want to maximize ELBO using parameters theta and phi, right? So theta being our encoder, phi, I think that's a phi, being our decoder. So let's go ahead and do that. So again, this is the most important takeaway from all of this. Because we cannot compute p of x directly, we have come up with an expression that we know lower bounds the log p of x. And as long as we can maximize this expression, then we will effectively solve our problem without ever directly having to compute p of x. And basically, if you ever take a random processes class or kind of do some more advanced math classes and probability, you'll basically see this is always the trick. This is always a trick. Like there's always something we can't compute, but we can somehow finagle some expression that will give us the same results without ever having to do that intractable computation. So now that we have that, let's go ahead and rewrite this in a way that makes a little bit more sense for our neural network. And so what we're going to do is this whole thing. What all we're doing is this. We're gonna split it up again. We're gonna say we're gonna call this one of the terms, and then we're going to call. Actually, no. We're gonna call this one of the terms, I believe. Yeah, we're gonna call that one term, and then this is gonna be the second term. So log of a times b is log of a plus log of b. So we're gonna use the same log trick like we always do. We're just gonna split some stuff up. So let's go ahead and do that. So first of all, this is going to be the sum, right? So it's going to be two terms, z element of z, q theta, z given x, log, we have pz over q theta, z given x, right? So that's the first term, plus, right? Now the second term, we just have that sum again, z element of z. We will now have our, again, just like before, q theta, z given x, and then we'll have our log of p parameterized by phi, right, because it's our decoder, x given z in this case. So that's our second term. And so we can go ahead and leave this alone for now. This is fine. Notice again, this is a sum over some distribution times some expression. So this is just expected value again, right? This is just expected value. And so we can actually rewrite this as, we can write it this way. We can write it as expectation over the distribution Q, right? Because that's what we're weighting by, of our log, and then we'll have P phi x given z, just like that, right? And this should start to look like the negative log likelihood loss. We're going to kind of see this later, but basically this is our reconstruction loss. How this is exactly a reconstruction loss, we'll see more specifically later, because when we do reconstruction, we actually don't use this form. We just kind of ignore it and just use mean squared error instead. And there's a relationship between negative log likelihood and mean squared error that we'll just briefly take a look at in the future. But for now, let's just call it the reconstruction loss. This is our reconstruction loss because you're doing, basically you want to generate x from z, right? So this is effectively a reconstruction loss. So for now, just kind of make this a little bit hand wavy. We'll come back to it later. On the other hand, what does this look like? We have effectively, this is our KL divergence. But notice in our KL divergence formula, right? Let's go back to the top here. In our KL divergence formula, we have P and then P in the numerator and Q in the denominator, right? So whatever we have on the outside must be on the numerator of the next thing. We don't have that here. We have Q and we have Q in the denominator and P in the numerator. So this is negative KL divergence, right? It's just flipped around. Negative KL divergence is this term. So we end up with our final expression, negative KL divergence, plus our reconstruction, right, is going to be less than or equal to the log of the thing that we want. And there we go. This is effectively what it is. And so this is our final loss. This is basically our loss function, right? That's all we need to do. And we could technically end here, but we want to find the final formula for all of this. So what we're going to do next, right? So this is kind of the end part. So this is the end of our ELBO exploration. What is the evidence lower bound? In the next part, what we're going to do is actually compute DKL specifically for a Gaussian distribution, for a Gaussian. So what does this look like for a Gaussian distribution? If you wanted to map to a different distribution that wasn't Gaussian, then you'd have to redo this computation, but it wouldn't be that hard. It'd be basically the same thing, just for a for something else, however you want to parameterize it. So let's go ahead and do that. So what we're going to do now is we're going to compute the DKL. I know there's a negative, but just ignore it for now. We're just going to do DKL. And we're just going to make this as simple as possible. We're going to do it between Q theta, z given x, which is the thing our model predicts. And just for shorthand, I'm just going to say P of z, right? So P of z, which we know is a standard Gaussian, right? Gaussian. So this is a normal 0, 1 distribution, and we'll do that part later. So again, let's go ahead and actually start writing things out. We're not going to do the normal 0, 1 just yet. We're going to just do the more general form, and then we'll plug in 0 and 1 later. So let's allow, or let's call Q, z given x, to be some predicted Gaussian distribution, and it will have some mu q and sigma squared q, right, for the q distribution. And then we're going to say pz is going to be some normal distribution with mu p and sigma squared p. And we know this should be 0, 1, but we'll again come back to that a little bit later. So in our DKL, our divergence, right, so DKL is going to be just the same formula from before. We're going to do the sum over, I'm just going to do shorthand, z, and then we will have q, and we'll do the z given x times the log of our q z given x divided by pz, right? So that's our same as before, just our KL divergence formula. Now for the annoying part. We know actually the formula for all of these distributions, right? We know the formula of a Gaussian distribution, and this is the part where I'm just going to assume univariate Gaussian, so not multivariate Gaussian. Otherwise, the expressions would just become too annoying to write by hand. So let's go ahead and write it out. So it's going to be the sum over z. So the first one, so this is a Gaussian distribution with 1 over square root of 2 pi, and it's going to be sigma squared q, because that's the variance of this one, e to the power negative 1/2, and we will now have x minus mu q over sigma q squared, right? So that's our first one. And then we're going to have the log of 2 more of writing all of this stuff out, right? So the first one's going to be exactly the same as before, so let's just rewrite it. It'll be 1 over square root 2 pi sigma squared q e to the power negative 1/2 x minus mu q over sigma q squared, right? So that's the first one. And then the second one is going to be the same thing. It's just going to have p's instead of q's because that's our distribution. So it's going to be 1 over square root 2 pi p. And then we're going to do e to the negative 1/2 x minus mu p over sigma p squared. But everything else is the same, right? It's just 3 Gaussian distributions, and that's it. So now time to simplify this super annoying looking thing. So the first step, let's just simplify the stuff inside the log. So this is again going to be sum z 1 over sigma 2 pi sigma squared q e to the power negative 1/2. It's annoying to have to write this over and over again, but it's fine. You can go through the video faster. Just put it on a faster speed and you'll get the same idea. But I'm going to just write it just so it's clear. So sigma q, so that's fine. And then we're going to have the log. And this is first the log of a over b, which we know is log a minus log b. And the log of e to the power something is just the thing that was in the exponent, right? So we can basically do all these simplifications now. This will end up being, let's take a look. We know that some of this will simplify. So the square root of 2 pi will delete. So we can get rid of that. And then the square root of the things will just become the things themselves. So it'll be sigma q and sigma p. And so there we go. So first of all, we're dividing, so it's going to flip. So we can first do a log of sigma p over sigma q, right? So that's the first term. Then we're going to do minus. And again, because we're doing log of e to the power something, it's just going to be just the exponent. So it'll just be minus. And because we'll have 2 of them, so we should be good. So yeah, it'll be just x minus mu. So we can do x minus mu q squared over 2 sigma squared q, right? So there we go. I just distributed the square out, and then we just have the 2 in the denominator, and we still have the negative sign. So that's the negative sign. And then similarly, the next one, it would be negative, but it's in the denominator. So because it'll be log, it's going to add, it'll become a positive. So it's going to be a plus. So we're going to have a plus x minus mu p squared over 2 sigma squared p. But everything else is the same, I believe. So I'm pretty sure that's correct. So that should be good. Also, notice here, all of this stuff here is a constant, right? There's no z's in it or anything, so we can actually pull it out. So this will just be 1 over square root 2 pi sigma squared q. So that's fine for now. And then we're going to have our sum over z. And we still have our e to the negative 1/2 x minus mu q over sigma q squared. So that's still there. And we still have the rest of this stuff, right? So log sigma p over sigma q minus x minus mu q squared over 2 sigma squared q plus x minus mu p squared over 2 sigma squared p. Oh, let's write that cleaner. 2 sigma squared p. Okay. And let's close the parentheses. And there we go. So this is basically our setup. Now, what you should see when you look at this is this kind of looks, this whole thing looks like an expectation of Gaussians, right? So what do I mean by that? This is our weight. Okay, so this, first of all, is a Gaussian kernel, right? So if you don't know, basically in every formula, if we go back to the top, if we look at our formula for the Gaussian or normal distribution, this is known as the Gaussian kernel. And and this is effectively just a scaling factor to make sure that our whole thing adds to 1, right? It's just scaling, so our distribution adds to 1. But this is effectively our Gaussian kernel. So this is basically an expected value on a Gaussian kernel that came from distribution Q, right? Z given X. So we can actually rewrite this in that form. And actually, technically, I could have just left this inside as well. It wouldn't have made any difference. But this is just an expectation. So what we have is a probability distribution. So let's actually make it clean and simple. Let's I know I pulled it out, but we don't need to do that. 1 over square root 2 pi sigma squared Q. This stuff, all of this stuff here, is a distribution that adds to 1 that we're summing over. And then this is the thing we're weighting. So effectively, this is still expected value, right? Expected value of X is just the probability, the sum over X, the probability of X times X, right? That's our simple expectation formula. In this case, this here is our probability of X. And this is the thing that we're weighting. So this is just an expectation one more time. So let's go ahead and treat it that way and just rewrite it along those lines, just to make it a little bit cleaner. So this is nothing but the expectation on Q, because it's the distribution Q. And everything on the inside is the same. We're still going to have a log sigma P over sigma Q. Let me double check that. Yeah, sigma P over sigma Q. Again, minus X minus mu Q over, and I made the parentheses too big, so let me rewrite that. X minus mu Q squared over 2 sigma Q squared plus X minus mu P squared over 2 sigma squared P. And that's it, right? So again, both of these expressions are equivalent to each other. I just wrote them differently because this is my distribution Q that I'm summing over. That's why it's the expectation over Q. And this is the thing that I'm weighting. And so there we go. That's the thing that I'm weighting. And that gives us, it's exactly the same as just writing the expected value. There's no difference. So now that we have that, we can start doing a little bit more simplification. First of all, log sigma P over sigma Q. This is all, sigmas are all constants, right? They're just constants. So we can just pull, we don't really care about it. So let's just distribute the expectation. The expectation of a constant is just the constant. So that's just going to be log sigma P over sigma Q. So there we go. Minus, the denominator here is a constant, right? It's just 2, but the numerator is not. So it's going to be the expectation of X minus mu Q squared divided by 2 sigma Q squared. So there we go. And then similarly, the last one's going to be the expectation of X minus mu P squared over 2 sigma squared P. And again, remember, these are expectations on Q, over the distribution Q. Now that we have that, let's go ahead and start doing some simplification. First of all, what does this look like to you? The expectation of X minus mu, where mu is the mean of X, squared, that's just our sigma squared, right? That's variance. This is just variance. This is our variance formula. And it's a variance formula because it's the expectation over Q. So we're doing the expectation over Q on X with mu Q. On the other hand here, this is the expectation over Q, but it's subtracting mu P, right? So this is not variance. This one's variance, this one's not variance. So let's go ahead and do that. So it's going to be log sigma P over sigma Q minus, like I said, this is just variance. So this whole thing ends up just being sigma squared q. And well, behold, we have a sigma squared q in the denominator as well. So if we have we can just cancel, right? These can cancel. And so all we're left with is a negative 1/2 in this case. After that, we have the rest of this stuff. So this is going to require a little bit more effort for us to simplify. And so we're going to see what that looks like in just a second. So we're going to do 1 over 2 sigma squared p. That's just a constant. And then we're going to do the expectation of x minus mu p squared, right? So now we have to deal with this, right? This is what we simplified because there's nothing really that we can do with it. So let's go ahead and try to simplify it. To simplify this, you have to do that age-old technique of add something and then subtract it again, and then use that to actually do the simplification. That's always annoying in math, so let's go ahead and do it. So the expectation of, with q, with respect to q, x minus mu p squared. What we know is that it'd be really convenient to have a mu q in there somewhere, right? We want a mu q in there somewhere. So if we want it, why not just introduce it? So we're going to do expectation q, and we're going to do x minus, so let's do double parenthesis, or actually, let's just keep it simple and I'll add that double parenthesis in a bit. Let's do x minus mu q, right? So it's mu p. So we're going to do minus mu q plus mu q minus mu p. So all I did is I subtracted something and added it back. So this expression is identical, and there's a square, of course, right? So because I subtracted and added, it's still the same. And what we're going to do, just to make it clear, I'll put a different color. I'm just going to throw some parentheses around here because there's no rule against doing that. And so what we really have here is some a plus b whole squared, right? We have something plus something, and we have a big square around all of it. So let's just go ahead and use our typical a plus b whole squared formula. So that's going to be expectation q, and so that's going to be the first thing squared. So it's going to be x minus mu q squared plus 2 times x minus mu q times mu q minus mu p, right? Plus that, plus the last thing squared, mu q minus mu p squared. And there we go. That's just me doing a plus b whole squared is a squared plus 2ab plus b squared, right? Nothing crazy. And so now let's go ahead and distribute our expectation through everything. So just like before, this is going to be the expected value of q of x minus mu q squared. Just like before, this is going to end up being our variance. This is going to be our variance, so we'll write that in a bit. Plus, we now have 2 and mu q minus mu p are both constants, so we can pull those out. 2 mu q minus mu p are constants, but x is not a constant, so it's going to be expectation of x minus mu q. So there we go. And then finally, we're going to have the expectation of this, but mu q and mu p are both constants, so there's really nothing to do. So we're just going to write mu q minus mu p squared. Oh, I don't need that. There we go. So that's our expression. So like I mentioned, this is, again, variance, right? Because it's expectation on the distribution q. We have the mean of q here, so it's all in q. So we can just go ahead and write sigma squared q, just like that. Minus, again, this is 2 times mu q, or sorry, not minus, plus mu q minus mu p. Now, what's the expectation of q of x minus mu q? Well, isn't this just the expectation q of x minus mu q, right? We can just distribute it out that way because mu q is a constant, right? So expectation of a constant is, again, just a constant. And the expectation q of x is just mu q. Well, we just did mu q minus mu q, which is just 0, which means this term here is 0. So this whole term goes away, right? Because we're multiplying by 0. So we don't have that anymore. So we don't actually have any of this anymore. And all we're left with is plus mu q minus mu p squared. So plus mu q minus mu p squared. And that is basically our simplification of this expression, right? So now let's go ahead and plug it back into our final expression. So all we did is spend time doing the work for this. So let's just plug it back in, get everything kind of nice and tied up. So our final expression is going to be log sigma p over sigma q minus 1/2, just like we had before. And then it's going to be plus, again, in the denominator, we had 2 sigma squared p, right? And then, like we computed, it's just going to be just this stuff right here. So it's going to be sigma squared q plus mu q minus mu p squared. And that is our final, this is basically our final formula. So we're basically done now, right? We're basically done now, except there's one more step that we need to do. Our p of z is a normal mu p equals 0, sigma squared p equals 1, right? We know it's a 0, 1 distribution because we want it to be set. You could obviously have it be anything you want it to be, but it's more convenient for something to be a standard normal distribution, right? Because why would you want it to be anything else anyway? So all we need to do is go through our formula, and for anywhere we see mu p and sigma p, just go ahead and plug in 0 and 1. So let's do that. So sigma p here is 1. So this is going to be log 1 over sigma q. Minus the half is still the half, so we can leave that alone. Plus sigma squared q is still sigma squared q, so we can leave that alone. Sigma squared q. In this case, we have mu q minus mu p. Like we said, mu p is 0, so it's really just the square of mu q, so plus mu q squared. And we're going to divide by 2, because this is just 1, so just divide by 2. And so we have a bunch of halves here, so let's just go ahead and simplify it. Let's pull a half out, 1/2. And so this will be log 1 over, and so if we pulled a half out, because it's a, we need to multiply this by 2, we can stick the 2 inside here, and so that means we're squaring it, right? Because of the log rule. So we can just square this here, and that's exactly the same thing. Because if this didn't have a half, so we'd have to do half times 2 times log, right? Just to make sure everything's the same. We can stick the 2 inside. There we go. There's the 2. We square everything inside because of log rules. There we go. This minus half will just become minus 1, plus these will just become individual terms. Sigma squared q plus mu q squared. And this is almost our final loss function, right? So this is equal to, so our final, again, let's go back to the very beginning. Where are we looking at? So our expression we're working with is this, right? Negative DKL plus reconstruction. All we have solved for is DKL. So let's put a negative on it at our reconstruction loss. And as long as we maximize this operation, this whole function, then we are meeting our ELBO loss, right? We're doing our ELBO loss. So let's go ahead and do that. So we need to throw, it's negative DKL that we need. So there's our DKL, right? This whole thing is DKL, like we computed. So we need negative DKL. So it's going to be negative 1/2 log 1 over sigma squared q minus 1 plus sigma squared q plus mu squared q, big bracket, plus reconstruction, right? Or in our case, it's at negative, like not negative, negative log likelihood. So let's just write that down. So this was going to just be our, this formula, expectation of log p x given z. So let's just write a shorthand for it. Expectation of log p x given z, right? So there we go. That's our shorthand. So this is what we're trying to maximize. We want to maximize this. Let's just stick the negative inside everything, just so it's clear. So if we multiply everything by -1, 1 over this will just flip. So this will just become log sigma squared q, right? So that's simplification. U will become a +1, and then both of these will become negative. So it's going to be negative this and negative this, plus our reconstruction loss. And what we want to do is maximize this, right? This whole thing is less than or equal to log p of x, right? This is ELBO. This is ELBO specifically for Gaussian, right? A Gaussian target. right? Or a Gaussian model that we want to do with our variational inference. So we want to maximize this, right? We want to maximize this with respect to all the, parameters of our encoder and decoder. Like in most neural networks, we don't ever actually maximize things, we minimize them. So instead of maximizing this, we just want to minimize, right? Instead we'll minimize the negative. Minimize the negative, all of this stuff. Negative log sigma squared q plus 1 minus sigma squared q minus mu. There we go. And then minus expectation log p x given z. There we go, right? So we want to minimize this. So minimizing the negative of this is the same as maximizing, right? So standard procedure for most neural network stuff. And this is our loss. This is effectively the loss function, especially this portion, right? This is effectively the loss function that we will be implementing in the next video for the variational autoencoder. Now, I do want to have a quick aside here, because I did mention that we typically don't. So this is clearly negative log likelihood, right? Negative, we have a log, we have a probability. So this is clearly negative log likelihood. We don't ever actually use negative log likelihood. We end up using mean squared error. So we'll do plus mean squared error as our loss function. I'm going to give a super quick explanation for why this is the case, though I don't want to go into too much detail about the relationship between some of these things. Okay, so just to give a quick idea, let's just kind of see where the mean squared error comes from. Though again, I'm not going to be digging into this too much today, which is fine. It's just to give a little bit of intuition. So we have probability of x given z, and our assumption is that this conditional probability is also Gaussian, right? This is another assumption made by the variational autoencoder that this is also a conditionally Gaussian distribution. So this means that really we're doing probability of x given mu sigma squared, right? Because we're z we know is Gaussian, so we're sampling x given a Gaussian distribution, right? So something like that. And so what does this again look like? We know the formula for a Gaussian distribution is just going to be 1 over square root 2 pi sigma squared e to the power negative 1/2 x minus mu squared over let's write it separately. So x minus mu squared over sigma squared, just like that. Right, so let's just quickly take the negative log likelihood of this. So what we're going to do is we're going to take the log likelihood. This is the likelihood function, right? This is what we have. So let's just take the log of it, basically. So this is going to be, and technically this would be for all samples. So, over the batch, if you have multiple samples, because it's a likelihood function. So we are just going to do the sum of the log and basically all of this, right? Px given mu sigma squared, right? Just like that. And similarly, the next step is just to simplify. So we just need to plug it in. The log of this is just going to be the log of this expression plus this numerator, or the exponent, right? Because the e to the power will go away. So all we'll be left with is effectively just something like, let's see, negative 1/2 log 2 pi sigma squared, I think. Yeah, that seems right. So that's the log. And then we will have, negative 1/2 because it's the square root. So yeah, there we go. So in the denominator, so that's our first term, minus, because it's a negative, it's going to be minus x minus mu squared over 2 sigma squared, right? And you basically start to see this term show up, right? Or that circle, this term show up. And this is effectively our mean squared error, right? The mean squared error between x and something that came from z. Remember, mu and sigma came from z, right? This is the mean standard deviation of z, something that we're trying to map to. And so this is slightly the reason why we can use mean squared error as our term, but and all of this is basically a constant compared to that, right? So we can kind of just ignore this, just use this, and it's our mean squared error scaled by something in the denominator, but we don't really care about it, right? So we use mean squared error as just a simplification, right? Just a simplification of the negative log likelihood. Obviously, using negative log likelihood is ideal. It's the more generic case, but mean squared error is a good estimation, or basically a good simplification of negative log likelihood when we're specifically dealing with Gaussian distributions, which is exactly what we're doing, which is why we're able to do this. I'm not going to go into too much more depth about that. The main takeaway is this, right? This is our final loss function that we will be implementing in the next video. So again, as a quick recap, right, let's just kind of go through the steps just so you have the big picture. We took a look at Gaussian distributions, right? So this is a typical form for Gaussian distributions. The autoencoder just compresses and decompresses, and we do the reconstruction loss, and that's it. The variational autoencoder, we compress and decompress. We still do the reconstruction loss, right? That's still there. But we add this new KL penalty that ensures that the encoded Z, right, our latent variable Z, is close to a standard Gaussian distribution. So the first step to showing this is figuring out, well, how do we get Z to be standard Gaussian? Well, Z is going to be some distribution, whatever it may be, and we know we want it to be standard Gaussian, so we need a way to measure the distance between the two distributions. And again, there's all sorts of methods that you can use to do this out there, but the most typical one is the KL divergence, right? The KL divergence is a good measure between our distributions, between two distributions. And KL divergence, like we saw, we can actually relate it to cross entropy and entropy, stuff that we have seen before, and we use all the time for neural network training, right? We see cross entropy all the time. So cross entropy, the relationship between two variables, is basically the distance between those two variables and the kind of the target variable itself. So there you go. Cross entropy is just your KL divergence plus your entropy. After that, I just wanted to quickly show that using Jensen's inequality, we can prove that KL divergence is always greater than 0. This is only necessary because we're going to use it in the proof later. So there we go. KL divergence is always greater than or equal to 0. The purpose of variational inference, again, is just to show that when we're dealing with complex high-dimensional distributions in this case, right, because we don't know what the distribution of our data X is, it's basically we have no idea, right? We don't know how to represent it, and we can't just come up with a nice formula that says, oh, this is a distribution of X. If you could come up with a nice formula, then we wouldn't have to do all this work, right? This wouldn't be necessary. So the variational autoencoder, or variational autoencoder being a method of doing variational inference, we attempt to map unknown distribution X to known distribution Z. And you can pick any distribution you want for Z. It's just Gaussian is the most typical one that we work with. So that's what we're doing. We map to Z. There we go. And so yeah, then basically the formulation, we just started deriving, showing, okay, so we want to find the KL divergence between the model's distribution, what it learned in the encoder, and the target distribution. And to do that, we use the KL divergence, we do kind of the derivation, we say that it's greater than 0, and we end up with the ELBO loss. And the ELBO loss is effectively just a formulation that says that this expression here must always be less than or equal to the log of the thing that we want, which means as long as we maximize our ELBO, we're maximizing the likelihood of the thing that we want, and they're equivalent operations. And this is, again, just a common trick used in statistics all the time. This is why if you ever take an advanced statistics class, you're going to start seeing things like the Chebyshev's inequality and the Markov inequality and this inequality and that inequality. And there's literally hundreds of inequalities, and they all exist just to let you be able to set up situations like this where, hey, I cannot solve this thing that I want, but I can solve this other thing I want, and this thing must be less than that. So it gives you kind of just a mechanism to solve these problems. We set it up. We then see that, okay, we can actually rewrite our ELBO loss is really just negative KL plus our reconstruction loss. And it's not really reconstruction, it's negative log likelihood, but we then, again, we don't really think about it too much. And so let's go ahead and solve for our KL divergence, right? So let's directly solve it for the Gaussian distribution that we want. If you wanted to do a different distribution, like a gamma distribution or an exponential distribution or a Poisson distribution, you totally could. You just have to redo this derivation for that specifically, and you'll do it for the parameters. So if you're doing it for Poisson, for example, you'd only have the lambda parameter, right? There'd only be one parameter in that case, and so you'd have to kind of pick and choose what you're working with. So let's go ahead and do it. We look at our KL divergence between our two distributions. It becomes this really annoying big formula of me just writing the Gaussian distribution a bunch of times, a simplification. This step was probably the most crucial one, right? Because we basically have to see that we're summing over a distribution times something, right? And so this is basically just expected value, just a very fancy looking expected value. So this is really just the expectation over Q times of our kind of expression here. And so once we do that, we can then actually solve. We see that this term is variance. This term does not become variance. So we have to do all this extra work to kind of simplify it down. We get this nice little form for it, for the expectation of Q with respect to x minus mu p whole squared. Once we have that, we can plug it back into our formula. We then get our final expression for our elbow loss, right? So this is again our elbow, just specifically for the Gaussian distribution. And now that we have elbow, we want to maximize this, but neural networks don't maximize, so we're going to minimize the negative of it. And like I mentioned, just with this quick aside, you can, mean squared error is a good estimator for, or basically a good simplification of negative log likelihood, and so that's why we use it when it specifically comes to these Gaussian distributions. And so I'm going to put a pin in it here. In the next video, we will be implementing all of this. So I'm basically going to just look at the formula and implement it. We're not going to really, dig into the math anymore. That's what this video is for. And so I'll see you in the next one.